For the reaction XY2Z2 gas produce XY2 gas plus Z2 gas described in part A. Gibbs free energies at 480 Kelvin for XY2Z2 gas, XY2 gas and Z2 gas are -60, -76 and -30 kilojoules per mole respectively. Question number 1. Calculate delta G in kilojoules per mole for the reaction at 480 Kelvin. 480 Kelvin is not the standard condition. Therefore, we will write the delta G expression. Delta G equals Gibbs free energy of products minus Gibbs free energy of reactants. Not using these standard symbols as the given temperature is 480 Kelvin. Now we will substitute values. There are two products. Gibbs free energy of XY2 minus 76 kilojoules per mole. Gibbs free energy of Z2 minus 30 kilojoules per mole. Then we need to subtract the Gibbs free energy of the reactant. It's minus 60 kilojoules per mole. Minus 76 plus minus 30 minus 106 plus 60. So the final answer is minus 46 kilojoules per mole. This is the Gibbs free energy change of the above reaction. Question number 2. The magnitude of delta S of the above reaction is 150 joules per Kelvin per mole at 480 Kelvin. Calculate delta H for the reaction at 480 Kelvin by using the appropriate sign of delta S. First, we have to find the sign of entropy change. The reaction is given here. We can see one reactant molecule produces two gaseous products. One gaseous reactant, it produces two gaseous products. In these type of reactions, entropy increases. For increasing entropy, we use the sign positive. Therefore, entropy change of this reaction is plus 150 joules per Kelvin per mole. Next, to calculate delta H of this reaction, we need to write down the expression for delta G. Delta G equals delta H minus T delta S. Again, the temperature is 480 Kelvin. Therefore, we are not using these standard symbols. The reason is this is not the standard condition. Now, we will substitute values for this equation. Delta G, we have calculated earlier. It's minus 46 kilojoules per mole. Then delta H minus temperature is 480 Kelvin. Then entropy change, it's 150 joules per Kelvin per mole. Now we can see the unit of delta G is kilojoule. Therefore, first we need to convert these joules into kilojoules. Now For that, you can divide this value by 1000, or you can write 10 to the power minus 3 kilojoules per Kelvin per mole. Next, minus 46 kilojoules per mole delta H minus, we can see Kelvin per Kelvin cancel out. It's minus 72 kilojoules per mole. Therefore, enthalpy change of this reaction is plus 26 kilojoules per mole. Question number 3. By using the sign of delta H obtained in question number 2, explain whether this reaction is exothermic or endothermic. Enthalpy change of this reaction is positive 26 kilojoules per mole. As we can see, delta H is positive. Therefore, this reaction is endothermic. This reaction is endothermic. Question number 4. Deduce the enthalpy difference for the formation of XY2Z2 gas from XY2 gas and Z2 gas at 480 Kelvin. Enthalpy change of the first equation is plus 26 kilojoules per mole. Now we will move to the second equation and check the similarities as well as the differences. Here we can see XY2Z2 gas is produced from XY2 gas and Z2 gas. The second reaction is the reverse reaction of the first equation. For these type of equations, the enthalpy change is the same as previous with the opposite sign. Therefore, the enthalpy change is 26. The sign is now negative. It's minus 26 kilojoules per mole. That is the answer for the question number 4. Question number 5. If the bond enthalpy of the XZ bond in XY2Z2 gas is plus 250 kilojoules per mole, calculate the bond enthalpy of the ZZ bond. Assume that XY2Z2 gas has the structure. The structure of XY2Z2 gas is given in the question. Now, we will write the previous chemical equation using their structures. First, XY2Z2 gas. It contains two XY double covalent bonds and two XZ single covalent bonds. Then the reactants XY2 and Z2 gas. Now, between the two Z atoms, there's a single covalent bond. We can assume that using the given question, it asks you the bond enthalpy of the Z-Z bond. Therefore, the covalent bond between Z-Z atoms we have to consider as a single covalent bond. We know the enthalpy change of this reaction because we have calculated during the previous question. It's plus 26 kilojoules per mole. And then the bond enthalpy of XZ bond. It's given plus 250 kilojoules per mole. And we have to calculate the bond enthalpy of this Z-Z bond. Now we can write the equation for delta H using these bond dissociation enthalpies. Sigma bond dissociation enthalpy of reactants minus sigma bond dissociation enthalpy of products. Or else we can draw a thermochemical cycle and using the Hess's law we can calculate this delta H. It's another method. But today I will use this method to get the answer. Now we can specify these bonds. Delta H equals reactants. Now we will see the types of the bonds we have to break. We have two bonds of X, Z single covalent bonds. We can write XZ. And then we need to add the other two bonds. So this is bond dissociation of XY double covalent bond. Again, number 2 because two bonds are available. From this value, we need to subtract bond enthalpies of XY. Again, two bonds of XY double covalent bond and one bond, it's ZZ single covalent bond. Now we can see this bond dissociation of XY double covalent bond, it's positive, and the right hand side we have negative bond dissociation of XZ. So these two values will cancel out and then we can modify this equation. Delta H equals 2 times bond dissociation of XZ bond minus bond dissociation of ZZ single covalent bond. Enthalpy change of this reaction is plus 26 kilojoules per mole bond dissociation enthalpies of this XZ bond it's 250, then 2 into 250 kilojoules per mole minus bond dissociation of the ZZ single covalent bond. Therefore, bond dissociation of the ZZ single covalent bond is plus 474 kilojoules per mole. That's the answer for the question number 5. If liquid XY2Z2 is used instead of gaseous XY2Z2, giving reasons, explain whether the value of delta H obtained for the reaction XY2Z2 liquid to produce XY2 gas plus Z2 gas is equal to or higher or lower than delta H obtained in question number 2. Enthalpy change when XY2 gas and Z2 gas produced from gaseous XY2Z2 is plus 26 kilojoules per mole. When liquid XY2Z2 is used to get the same products, enthalpy change we will assume as delta H1. To complete this thermochemical cycle, we need the enthalpy change of vaporization. That is, enthalpy change when liquid XY2Z2 converts to gaseous XY2Z2. Always vaporization enthalpy is positive. It's endothermic. According to the Hess's law, we can write delta H1 equals delta H, or we can write plus 26 kilojoules per mole plus enthalpy change of vaporization. Therefore, we can see enthalpy change of this given reaction is greater than 26 kilojoules per mole. In other words, this new enthalpy change is greater than the previous enthalpy change delta H. So it's higher than delta H. That is the answer for the question number 6.